conformal gap theorem of H4.
Thank you for the invitation. It's an honor to give a talk in the Geometry Center. So I want to talk about some conformal gap theorems on S4 and CP2. And first, let me start with a sphere theorem. And we geometers or mathematicians are fascinated with the sphere and want to know what manifolds are diffeomorphic to sphere. And of course, there are lots of work about homeomorphic and diffeomorphic to sphere. But let me just mention a couple more recent results. One is this famous result of Brendel and Rixian, where they characterize sphere using the quarter pinching theorem. So the quarter pinching theorem is a pointwise condition on the sectional curvature. If that's pinched between 1/4 and 1, then using the Ricci flow, it flows to the fourth sphere, to the n sphere. But in this talk, I want to emphasize situation on 4 manifolds. So let me mention results in this direction. So there's this result of Hamilton, 1986, where he says that if the curvature operator, the curvature Rijkl, if that's positive, so in here, the curvature operator is considered to be a bilinear operator on 2 forms. So that's defined to be on the 2 form is on phi psi, this tensor Ijkl, phi ik, psi jk. Psi jl is positive for all phi psi. Under this condition, he again used Ricci flow to flow things to fourth sphere. But now I want to mention another result which is less long, and that's a result of Magellan. Magellan viewed the curvature in another way. What he thinks is, now we look at the curvature decomposition as a 4 tensor. Now it's split into 2 parts. One is the Weyl curvature part, and the other is what we call shortened tensor part. The shortened tensor is a combination of Ricci and scalar, but that's a very special decomposition. It's Ricci minus a multiple of the scalar. And then the curvature Rm is decomposed into 2 parts. And in 4 dimensions, this shortened tensor, now for my purpose, I split into traceless Ricci part, that's by notation E, plus a multiple of the scalar curvature. So the full curvature tensor now is 3 parts. One is the Weyl part, the other is the traceless Ricci part, and then the scalar part. So that's a curvature decomposition. So Magellan's idea is he considered a pinching between the first 2 terms vice the scalar curvature term. So he considered a condition called the weak pinching condition. So the weak pinching condition is the norm of Weyl square plus 2 times E square divided by the scalar curvature square. So weak pinching, his theorem is the following. He says that if the weak pinching constant is less than 1/6, then the manifold is diffeomorphic to fourth sphere. Again, he used the Ricci flow to show that this weak pinching condition is monotonic, and then it's a flow to the fourth sphere. And then he also says that this 1/6 turns out to be sharp. And if 1/6 happens, then number, this manifold, if it still can be diffeomorphic to the fourth sphere, but if it's not, then there are two cases. One is it's conformally equivalent up to a conformal change of metric. It's the same as S1 cross S3, the standard product, or CP2, the Fubini study metric. Okay. And let me just say, S1 cross S3 happens when the Weyl curvature is identically vanishing. Okay. And in the other case, it's CP2.
It's actually a modular space of different component structures where S1 times S3, so it might not be the product metric. It could be, a universal coverage that's 3 times.
That's right, that's right. Yeah, I'm talking about simply connected case. I'm sorry, yeah. And so the proof, again, using Ricci flow. Okay. And let me also mention there are results of this type also in n dimension, but only in 4 dimension, Magellan's result is sharp. Okay. So this 1/6 constant is sharp. And now, the point of view we are taking now, if we look at, again, this curvature decomposition into Weyl part, traceless part, and scalar part. But the Weyl curvature has one special good property, that it is almost pointwise conformal invariant. So that means if I look at a change into a metric, I denote that by exponential 2w, and then this Weyl pointwise they move to this. So this part is the pointwise conformal invariant part. So that suggests in the curvature decomposition, the comparison should be between Weyl part and the shortened tensor part. Okay. So for this, we introduce the following notation. So we look at the shortened tensor, and then we begin to look at its second elementary symmetric function of its eigenvalue. So that means this shortened tensor PG, and we look at it as a 4x4 tensor and look at the summation lambda I, lambda j. And that turns out to be a multiple of the scalar curvature minus the traceless Ricci square. Notice the negative sign. Okay, so the negative sign. So an observation made in our early work is we notice this weak pinching less than 1/6 is algebraically, if and only if the Weyl part is compared to this sigma 2, the second symmetric function of this shortened tensor. So this is an algebraic computation. So that's why are we interested in this Weyl square compared to the sigma 2? And that's because on M4, if we consider the functional 1 and 2, one is this integration of Weyl square, and the second is this sigma 2. I have already mentioned that under conformal change, this square, Weyl square d volume, is a pointwise conformal invariant. So the integration is a conformal invariant. That is, the Ig hat is the same as Ig. But it turns out this second functional is also a conformal invariant. So in that case, this sigma 2 dvg is not a pointwise invariant, but the integration is a conformal invariant. So it's the analog of Gaussian curvature. Gaussian curvature on surface is not a pointwise invariant, but integration of Gaussian curvature is a topological quantity, hence it's conformal invariant. And to see that, and this is a consequence of Gauss-Bonnet. So in compact 4 manifold without boundary, the Gauss-Bonnet is written as 1 plus 4 times this 2 functional. So if 1 is conformal invariant, this is topological, then the second thing is conformal invariant. And for the rest of the talk, let me denote this Weyl square in this double line norm to be 1/4 Weyl square. And this has the meaning that when I use this Weyl norm, this is a tensor norm, 0,4 tensor. But this double norm turns out to be the norm as the endomorphism from two form to two form. Okay. So this is the endomorphism norm. Okay, so based on this observation in the early days, we have the following theorem. We say that the Majorcan theorem really has an integral form. Okay. We say that if we assume that this 4 manifold is in the positive Yamabe class, the scalar curvature is positive, and then also if this conformal invariant quantity integration sigma 2 is positive, both are positive, then if this first functional 1 is less than 4 times sigma 2, instead of saying the pointwise condition of Weyl square to 4 sigma 2, we say if it's integral, then the manifold is already diffeomorphic to 4 sphere. Okay. So changing the pointwise condition of Majorcan to the integral condition. And it turns out this inequality is also sharp. When it's equal, and if the manifold is not diffeomorphic to S4, then we can pin down to say it's already conformal equivalent to CP2. Okay. And notice I have skipped the case of S1 cross S3. And that's because in my condition here, I already assume the integration of sigma 2 is greater than 0. Okay. So the Weyl never vanishes. Maybe I should say greater than 0. I assume integration sigma 2 is positive. S1 cross S3 turns out to be the only manifold in the class I consider which has integration sigma 2 equal to 0. Okay. So this is the theorem. Okay. And so let me mention a couple of points in the proof. One point, the first point is this is really a result in folding the linear PDE. One key point is if we change the metric from G hat to G, then the sigma 2 of PG hat is sigma 2 of hashing of this conformal factor W plus a lower order term. So the study of sigma 2 of PG hat is like the study of sigma 2 of hashing. So we use that to move the integration from the integral condition to pointwise condition. Okay. The second point I want to make is if we are looking at the second condition, so how do we pin down its CP2 and when the integration is equal? And that is, at that point, we also assume the equality holds and the manifold is not diffeomorphic to S4. So that means that in the case of the functional integration Weyl square, if that happens, then that metric must be a critical point of the first functional, the integration of Weyl square functional. So that means that if the case 2 happens, then the metric satisfies an additional condition, and that's the critical point of the Weyl square functional, that's the Buck-Flag condition. So this Buck-Flag condition is, in some sense, a fourth order condition on the metric, or it's the second order, the Weyl, and plus Ricci Weyl. Okay. So this B equal to 0 gives us an additional PDE to play with. Okay, so this was work done many years ago, and we have not continued to work, but at the back of my mind, this is my favorite project. So we recently picked it up again. So the goal is to extend the theorem above to a class of 4 manifold such that these 2 conformal invariant quantity are positive to extend above theorem. So let me mention some basic results in this class. Okay. So the first result I like to mention is that in the work of Gursky, early work of Gursky, we already observed that under this condition, this integration of the second invariant has a natural upper bound, 4 pi squared. Okay. And that's attained only on standard force field. So the second quantity has a bound. And then we also notice that these two conditions add up did give some topological information of this class of 4 manifold. Okay. And one condition is, and the first Betti number is going to be 0. Okay. And the second condition, it says that under this invariant condition, these two constant positive, actually using this PDE method, we know in the same conformal class, we find something whose scalar curvature is positive and sigma 2 is positive. We say it's in positive 2 cone. Okay. And it turns out metric in positive 2 cone algebraically also has the nice property its Ricci is positive. Okay. So in this class of manifold, we have finite fundamental group. Okay. Finite fundamental group. So they are topological consequence of these two conditions. So now let me briefly mention a class of manifold which satisfy these two conditions. And of course, there is the fundamental work of Donaldson and Friedman, which they provide a list of simply connected 4 manifold under the condition scalar curvature is positive. So these are up to homomorphism type 2 class, the K copy of S2 cross S2, and then the K copy of CP2 and conjugate with the connection with this L copy of CP2 conjugate. So one is spin, one is non-spin. So among this class of manifold, since we assume Yamabe positive, we already are in a scalar curvature positive class, and we can directly check if K is bigger than L, assume the orientation is K is bigger than L, then 4 plus 5L must be greater than K in order for these two constants to be positive. So for example, when L equal to 0, K should be less than 4. Okay. And it turns out there is also the work of Claude Laboon and Nayatani and Nita, which says that K copy of CP2 for K less than equal to 3 actually admits such a metric, Shelf dual sigma 2 positive scalar curvature positive metric. So these are among the class of examples where this apply. And now let me also say that there are other obvious examples. CP2, where we already know the Weyl square is 4 times sigma 2. And then S2 cross S2 has this integration, this functional Weyl square is 8 times sigma 2. And then, of course, there are these examples. If you have CP2 and connection with L copy, and if L is between 8 and 3, there exists Kähler-Einstein metric. So this belongs to our class. And in this class, one can compute the Weyl square ratio to sigma 2. There is this R1, R3, R4, and so on. This is L. RL, sigma 2, R3, and so on. And it's an increasing sequence. So these all are the examples for our class.
In the
the list of homomorphism types, why don't we have K not equal to L?
Yes. I think we have the assumption K not equal to L to be oriented or not oriented. Is that right? I may be wrong. I'm quoting your theorem. Yeah. K can be equal to L. I'm sorry. Then yeah. Maybe K can be equal to L.
So in particular on this list, they're not Kähler-Einstein, but formally Kähler-Einstein metrics. CP2 connected some CP2 bar.
Yeah.
K and L both 1, or K equals 1 and L equals 2. Those also exist.
Okay.
Yeah.
Thank you. Pointed out. I need to check. For some reason, I write K not equal to L. Maybe it's because in my class there is constraint. Okay. Yeah. Okay. Sure. Yeah. Okay. So I'm just trying to quote some result. Okay. So now let me mention some topological result. Okay. Suppose we look at the ratio of these two functional, and we call the ratio beta. Okay. Then we already know if beta is between 1 and 0, the manifold is diffeomorphic to the force field. And if it's equal to 1, then it's equivalent. It's actually CP2, conformally equivalent to CP2. But if we look at the next one on the list, when beta is between 2 and 1, it turns out one can see that there are only two homomorphism type. One is S4, one is CP2. Okay. And this number beta equal to 2 is sharp, because at beta equal to 2, you have S2 cross S2. Okay. So the next on the list is when beta is between 2 and a little bit bigger than 2. It turns out the number we can get is 9/4. And that corresponds to 2 copies of CP2. But we do not know if the constant is CP2, the metric you construct, is really reach 9/4. Okay. So this constant we are not sure. But in this class, the manifold there are 3 possible homomorphism types. And this topological result is observation coming from the Gauss-Bonnet theorem and the index formula. Okay. And because in our class of manifold, this second functional integration sigma 2 already has a natural bound 4 pi square. So there is some ratio, constraint on the ratio. Okay. And the signature formula, there is the Schoff dual part of Weyl square minus the anti-Schoff dual part of the Weyl square. So combine this, we get a topological result. Takes some work, but it's basically observation from these 2 formulas. Okay, so looking at the list above, a question we are trying to see is, after S4, what is the next step? Okay. And it seems to us that a natural question to ask is, if the ratio is between 2 and 1, so this first functional and the second functional squeeze between 1 and 2, we are asking if the manifold is either diffeomorphic to S4 or diffeomorphic to CP2. Okay. So we are asking if that's true. We are very far from answering this question. And the basic question is, so far in the flow method, we treat Weyl square as Weyl plus square minus Weyl minus square, and we do not split them. And when we deal with CP2, we need somehow to have a method to split the role played by the Schoff dual part, anti-Schoff dual part. So we are far away from proving this theorem, this result. But today I want to report some very small progress made in this direction, a joint work with Gursky and Siyi Zhang, who is here. Okay. So now let me first go back to S4, okay, and talk about gap theorem on S4. So on S4, we have this, the standard S4 has the second functional is 4 pi square. And in the early work, we also say that this 4 pi square has a gap. Okay. So that means that if it's close to 4 pi square, we want to say it's conformally equivalent to S4. But we do not reach it. We really say that if the metric is already Bach flat and with Yamabe constant positive, then this is the case. We are willing to add Yamabe constant be positive, but a Bach flat is an additional assumption. So under the class of Bach flat, then we know there is a gap. And this theorem was first proved under the additional assumption. We already also assume some topological bound. That is, we assume the Weyl square has a constant, positive constant bounded above. And this condition was later moved by the work of Li Gang, Qing Jie, and Si Yuguang. And they moved this condition by applying the recent work of Chigger and Neighbor, the codimension 4 conjecture. So this condition was removed, and we have a gap. Okay. So given this thing, a recent work, the first theorem I want to report is the gap in this case. If we know it's topologically S4, the gap is really 1/2. So that means that if sigma 2 is greater than 2 pi square, then it's already S4, the standard S4. Okay, there's a gap. And one of the reasons we are interested in the gap here is, I don't know, in this field there's one problem which fascinates us, and that's as far as we know, it's still an open question, and that's on S4 if there are other positive Einstein metric other than the standard S4. Okay. And our theorem, a consequence of our theorem is if G is Bach flat, and which is a class larger than the Einstein metric is Bach flat, then this thing is already less than 2 pi square. So we would like to use this invariant, this size of this sigma 2 to control the metric, and that's the goal. And it turns out there is another result of Gursky, which says if you are under this assumption, del Weyl plus is equal to 0, then the size of this invariant is even less than 2 pi square. This size, del Y plus equal to 0, is also a class bigger than Einstein. Okay. So we are playing with this condition and trying to control the size of this functional. So now the second result I had to report is a little bit of a gap theorem on CP2. Okay. So this B2 plus, of course, is intersection from intersection theory, but let me think about it as a dimension of the Schoff dual part of harmonic twofold, Betti number. And so what we say is there exists an epsilon. If this, we like epsilon to be 1, but we don't know. So if there is some epsilon, if this comparison is between 1 plus epsilon to 1, then it's conformally equivalent to CP2. But again, we need to add some condition for us to work. One is the bar flat condition, an elliptic condition to help us. And the other is we also add the important, this assumption. We assume that this B2 plus is already greater than 0. Okay. And it turns out under this constraint, the size constraint, the B2 plus positive really is saying B2 plus is already 1 and B2 minus is 0. Okay. So it's already a homomorphism type of constraint. So this is the second theorem. Okay. And for the rest of the talk, I will begin to describe some sketch of how to prove theorem and 1 and 2. But before I do that, let me briefly mention some other work which Rubin, Zhang here, and Paul, Yang, and I are working on, which is related to this problem. And the work we are interested in is the finite diffeomorphism type of result. Finite diffeomorphism type. Theoretically speaking, we are mostly interested to see under this class, this constraint, the Yamabe constant positive, the invariant constant sigma 2 positive, that if there are only finite diffeomorphism type result. And we not able to answer that, but in early work, we have the following theorem modeled after Chigger and Anderson theorem. We say that if in this 4 manifold, if the vial has some bound, L2 bound, and if this sigma 2 is more than greater than 0, if it has a positive lower bound, then we reach finite diffeomorphism type. Okay, changing the finite diffeomorphism type. And in view of the recent work of Chigger and neighbor, it is most natural to ask if, again, in this case, this topological assumption, the L2 norm of vial square is bounded, if that condition can be dropped. Okay. But it turns out this is quite a difficult question for us. And instead, we are beginning to study sequence of metric with sigma 2 g equal to 1. Okay. So let me recall this sigma 2 g is really a cancellation term. So there is a 1/4 r squared minus e squared. Or up to suitable constant is really square minus 3c squared in 4 manifold. And so the question for us is, if this thing is positive, if scalar curvature is positive, if this thing is positive, then Ricci is already positive. But on the other hand, Ricci or the scalar can blow up. There is this difference. So we cannot tell if this condition prevents scalar curvature to be blow up. So if you rescale this to make the curvature bounded, then Ricci is bounded above and below for the rescaled sequence, but then this sequence of the rescaled G becomes degenerate. It becomes sigma 2 of G equal to 0. Okay? So you are beginning to study this degenerate elliptic PDE, which is quite difficult. And at this moment, we are still studying the blow-up phenomena of this degenerate PDE. Okay. So this is ongoing work. Okay. And for the rest of the talk, let me briefly mention how to prove this theorem. Okay. So the tools we are using in proving this theorem. So in the proof of theorem 1, we are saying that if it's bar flat, and if this integration is greater than 2 pi squared, then the manifold is S4, standard S4. So how do we see that? Okay. First, this on S4, then we have this Gauss-Bonnet. The left-hand side becomes 16 pi squared because Euler characteristic equal to 2. So this assumption, this thing is greater than 2 pi squared, is greater than this, is equivalent to say the functional 2 and 1 is great. So that means that you can choose a metric such that this is equal to the Weyl square plus something positive, some delta positive. So let me rewrite this sigma 2g, and it's scalar minus 3c squared. So this equation gives you a pointwise relation between scalar, traceless 3c, and Weyl, some control of the norm. And now we look at why do we need a bar flat metric. For bar flat metric, we can derive some Weizenberg type formula. Okay. And when deriving it, we keep in mind the suitable norm to consider could be the curvature, the operator norm, or the decomposition into this single entropy theorem. So there is two formula. One is a derivation of traceless 3c squared minus the energy, gradient E squared minus gradient R squared. And then the left-hand side has a WEE term. So this is derived by looking at Laplace sigma 2 equal to 0 with bulk tensor equal to 0. And then there is a second equation, and the second equation really split the Weyl plus with Weyl minus and look at its determinant. So this is looking at it as an operator from two form to two form, positive two form to positive two form. So it derives that. Okay, so using Blackboard really is better. So what we do now is we look at the PDE we are having. That's our PDE. From PDE, we derive a relation between this, the energy of this E, R, and Weyl. This is equal to that, means this is positive. And that positive means the left-hand side of 1 plus 6 times the left-hand side of 2 is positive. So that means that's the left-hand side. The right-hand side of these two add up should be positive 2 because they are the same. And now notice we have some pointwise relation between Weyl, scalar, and E. So the rest of the proof actually says that if you examine the integron of the right-hand side very carefully and using these are the Weyl plus, Weyl minus, and E all are traceless tensor. So for example, the 3 eigenvalue of Weyl plus add up to be 0. So that means in estimating this, there is some constant which you gain. And it turns out that integron is actually the right-hand side integron cannot be positive when delta is positive, unless while is identically 0. Okay? And the proof actually becomes delicate when delta equal to 0. When delta equal to 0, you begin to allow the situation of CP2. That is, while plus is non-zero and while minus is 0. Okay. So, but when, in this case, when delta is positive, that forces while to be vanished. So that is the reason of the proof of the theorem. Okay. So now let me say a few words about the proof of theorem 2. Okay. So the proof of theorem 2 is if we assume this self-dual part, the second Betti number is positive, and the metric is bar flat, then under this pinching condition, integral pinching condition, we want the manifold to be CP2. So how do we see that? Okay, it turns out that in this, so far we have used two representatives in the conformal metric G, the two most frequently used ones. One is this Yamabe metric, which has the advantage is scalar curvature is constant. And in all PDE, this is very easy to use. And then we have also used this sigma 2 metric, which has the advantage tell you some pointwise relation between while and this E and R, scalar and E. And one of the problems of using this sigma 2 metric, say equal to some multiple of while square, is that in this case, the while square only control the gap. We do not know if the while control the size of the scalar. Okay. And it turns out this control is provided by some work of Gursky and the Boone. Okay. So we are going to use this condition B2 plus positive to have another control of the conformal class, and that's using the work of Gursky and Boone. So what they did is the following. It's their early work. So what they do is they say that in full manifold, one should consider another generalized Yamabe problem. And that generalized Yamabe problem is, instead of consider the conformal Laplace G plus 1/6 scalar curvature, one should consider scalar curvature minus a multiple of while plus curvature. And because while plus has this pointwise conformal invariant property, the corresponding linear function, this functional, again, is conformally covariant. So the whole machine of achieving Yamabe metric can be applied here. And the offshot is, in this case, one can get in the same conformal class a metric which is FG theta plus is constant in general. Instead of solving scalar curvature equal to constant, we add this while plus square. So what has that to do with this B2 plus positive? If B2 plus is positive, then in that case, if you have a harmonic 2 form, then there is a Weissenberg formula. That's a Laplace phi square and gradient phi square minus 2 plus and plus 1/3 R. It turns out, remember we are considering this scalar curvature minus 2 square root of 6 of while plus. And this 2 square root of 6 comes in is because of this while plus has cancellation property. If one wants to estimate this middle term, one gets a constant. So if this constant, this is my f, so the offshot is if this f is positive, then the harmonic form phi must be 0, identically 0. So the existence of a non-trivial harmonic 2 form means the f you attempt must be negative. So there is a negative constant such that this metric for G Tirita metric is negative, B2 plus, positive implied. There exists a metric, this is negative. This is negative, okay? And this negative tells you this vial plus for this representative actually control the growth of scalar. Okay? So that's an additional control we have about the manifold. And using this, one get the following consequence. In cope with this theorem, under the assumption of the theorem 2, first, one can see the Yamabe constant of the metric is already close to the Yamabe constant of CP2 under this pinching condition. And then the second thing one can see is vial square is already less than C epsilon. The L2 norm is small. And then applying this Gursky-Lebon's result, one can see the E, the L2 norm of the G Tirita, this metric square, is less than 3 times that. And then that's less than epsilon. And in this case, the G Tirita metric, turns out we have other difficulty of using it directly, but once its L2 norm is small, the Yamabe metric, the L2 norm is the smallest one. So it's also less than epsilon. Okay. So this first and A and B are consequence of this assumption of the theorem and the signature. This third C actually comes from applying the result of Gursky and Lebon. So then we can come back to prove the theorem. Okay, so let me recall the theorem is we want to say that under this pinching condition, the manifold is already CP2. So we say if it's not, then you have a sequence. And the sequence is such that this sequence of manifolds such that this Yamabe constant is close to the Yamabe constant of CP2. And then we have the additional assumption is Ricci, traceless Ricci tend to 0. Okay. So from there, again, we use the assumption of Bob flat. Okay. So in this case, there is an early work of Chang and Vygotsky. They study the limiting of Bob flat metric, and also Michael Anderson. And then we get the rescaled metric of this sequence begin to converge. And that converge is to an orbifold metric with orbifold singularity. So what we do now is we say that, we begin to say that the limiting metric is Ricci flat due to this condition. And then we know the limiting metric has this Yamabe constant. And this Yamabe constant is very close to the Yamabe constant of the flat metric, sufficiently close to disallow the orbifold singularity. Okay. So the offshot is, in this case, the limiting space is actually flat. It's R4. Okay. And then from there, one can show that this is actually Schoff dual Einstein. The limiting metric is Schoff dual Einstein and CP2. Okay. There is some work here. One doesn't need the whole result of Hitching. In this case, because we have enough topological information, one can see that 3C2 minus C1 squared is equal to 0. And from there, one can conclude it's CP2. Okay. So after that, if the limiting metric is CP2, we actually can come back to say the original sequence already is CP2. Okay? And that, again, we look at the Weil minus square, this Weissenberg formula. Okay? And from there, and since this Weil minus, the limiting metric is 0 and the converging is smooth, so this Weil minus is small, pointwise small. And then somehow the E squared known, the L2 known is bounded by Weil minus L2 known. So the whole thing squeeze Weil square minus to be 0. And so it's again CP2. And that means that with the contradiction says the original thing is already CP2. Okay. And so the two remarks I would like to make is first, the Bach flag condition there is to help us to have an elliptic PDE to play with. And it is natural to think that, to hope that this Bach flag condition can be replaced by some other parabolic type condition, like flow. Okay. So the hope is remove the Bach flag condition, but prove the theorem. In that case, one cannot expect the manifold to be conformally equivalent to CP2, but one hope the manifold is still diffeomorphic to CP2. Okay. So that's the step we are working on. Okay. So using flow method to replace this Bach flag condition. But a much more challenging problem for us is how to remove this topological assumption that we already assume in this theorem. There's a Betti number assumption. We use the Gursky metric very critically, and we do not know how to. I think it's challenging to eventually to prove the diffeomorphism theorem to see how to remove this condition, and that we do not know yet. Okay, sure. That concludes my talk. Thank you.
Other question?
So when you impose the condition that you have a uniform L2 bound on the Weil tensor, if you so is that you're going to eventually deduce from that you have these Bach metrics and want the integral of sigma 2 to still be positive. Right?
Yeah.
Right?
Yeah.
So it might be useful to know that, for example, just on S2 times S2, there's a sequence of Bach metrics where the L2 norm of Weil goes to infinity.
Yeah.
So I mean, this is harmless from your point of view because the integral of sigma 2 must become negative.
Yeah, yeah.
But I don't think this is artificial assumption. I think
That's right. Actually, in this case, this is related to study this limiting metric of this thing. We do encounter into the situation of either it degenerate to S1 cross S3, or the other possibilities, S2 cross S2, which we have not been able to. We are still studying. So you are right. You want to say there are more and more copies of the Weil square comes into the limiting metric. Yeah. Okay. Yeah.
Other question?
You have this different ranges for the Roberts and I before, I think.
Yes.
Do you have a guess of what the next range would be?
Oh. Yeah. Yeah, it's this range. This order is according to the size of the Betti number. So in the first case, everything is 0. All Betti is equal to 0. In the second case, we have B2 plus equal to 1, B2 minus equal to 0. And now for S2, we have 1, 1 case. And then this case, again, we guess it's CP2, direct sum with CP2. So, so the problem is with this 2 copy of CP2, we do not know the precise ratio between the existence of a matrix does not allow us to compute the precise ratio of the 2 functionals. So at this moment, yes, that's right. That's right.
So the page metric is, I think, the next one. It'll be just a little. It will be slightly larger than 9 quarters.
Yes, yes, slightly larger, but you know if it's.
Yeah.
You do not know in a connection. We know that the Weyl square is a connection too, but we do not know if that's exactly the minimum one. So it's something we are thinking about, but we haven't got it. So if that's the case, then we try to see what's next one. So at this moment, we do not know if this is the right one.
So for that particular example, it's the ratio is not rational. It's the root of the following equation.
That's right. That's right. So yeah.
Compute it for you, but it's not clear that it's the next one.
Yeah.
But it's not much bigger. It wouldn't be much bigger than 9 quarters.
Yeah. Well, we can approximate. We cannot say that's exact. That's exact. Yeah. Sure.
Maybe I have a remark. That 9/4 is actually for the shelf-2 metric on the connected sum of CP plus CP2. And there is a metric which has positive sigma 2, which was constructed by the work of the friend.
That's right.
That is the 9/4. But we don't know where to put the other example. There is an Einstein metric on CP2 connected with the candidate of CP2. Open and take. And there's another one with CP2 connected with 2 copies of candidate CP2. That is not Taylor Einstein, but it's Einstein. So we don't know where to put it.
Yeah. Yeah.
So,
yeah. Of course, the challenging question for us is if the disk is actually finite or infinite. That we don't know. That we don't know. We hope it's finite, but but we don't know. Yeah. Uh-huh. Okay.
Questions? Nothing again?